In this video, we're going to describe the Gaussian mixture models algorithm. Before that, we're going to provide a brief revision for the multivariate Gaussian distribution, since this is the basis for the GMM. So in this equation, in this first equation, we see the form of the univariate Gaussian distribution. The univariate Gaussian distribution is parameterized through a mean, which is the part of the distribution that for which most of the values are concentrated, and the standard deviation or the square of the standard deviation, which is called the variance. And this refers to how widely spread this probabilistic distribution is around the mean. So this is the one-dimensional version of the Gaussian distribution, while we also have the multivariate version, which refers to having more variables as part of the input of that Gaussian distribution. So the variable space here can be a d-dimensional variable space, and the multivariate Gaussian distribution is parameterized by a mean, which is a vector that has as many elements as the number of variables of the Gaussian distribution, and the covariance matrix sigma, which is a square matrix, and its dimensionality is again as many variables as the number of variables of the Gaussian distribution. So here in this example, we see a two-dimensional Gaussian distribution where x and y axis correspond to each two variables, and here the z-axis corresponds to the result of this Gaussian distribution. Again, we see that the shape of the Gaussian distribution can reflect its mean. So its mean here, it's a two-dimensional point that corresponds to the peak of the z-axis on the x and y dimensions. And then we can also see that the amount of spread of the Gaussian distribution is being represented by its covariance. We're going to provide a little bit more details now about the covariance of the Gaussian distribution and how it determines its spread. So the covariance of the Gaussian distribution, as we said, it's a square matrix of dimensionality d times d, where d is the number of variables of the Gaussian distribution. Its diagonal elements are all 1 because its diagonal elements reflect essentially the covariance of each variable with itself. But the non-diagonal elements reflect the covariance of each variable with another. So if we have variables xi and xj, the covariance between the two. The covariance matrix is always symmetric and always positive definite. So a way to better visualize the spread of the multivariate Gaussian distribution is what we call an isocontour. And especially in this case that we have a two-dimensional Gaussian distribution, the isocontour reflects, is a set that reflects how the percentage of samples that are in each area of this two-dimensional space. So again, imagine that the x and the y axis represent the two variables of the Gaussian distribution, and here the color coding represents the percentage of samples that can be found in each x and y coordinate. So here we can see that in that center, just because we have a higher concentration of samples, we have a darker red color, while the more further away we go from the center, the more this color becomes lighter, and then it becomes darker blue. We see, though, what is good about that is that we can see the directionality of the samples, which is very similar to the overall structure of the covariance matrix. So if we go in this example here that also shows the isocontours, for this first example, we see that we have two variables that have the same spread. Therefore, the corresponding covariance matrix will have the same elements across the diagonal elements. And we also see that in this second example, we have a larger spread across the x2 axis and a smaller spread across the x1 axis. That is why the first element here is smaller, and this second element, this element 2,2 of this covariance matrix is larger. Also, the opposite happens when we have larger spread across Y1 and smaller spread across X2. This is an example where X1 and X2 are not correlated with each other. That's why the non-diagonal elements are 0. However, in practice, we can also have examples in which X1 and X2 are correlated with each other. In this first example here, we see that X1 and X2 are correlated because the isocontour is a little bit tilted on a 45-degree angle. And therefore, these non-diagonal elements of the matrix are close to 0.5. Here we have a higher correlation between these two variables, X1 and X2. That is why these non-diagonal elements are close to 0.8. And finally, here we have a negative correlation between X1 and X2. That is why these non-diagonal elements are approximately close to -0.5. Now, why is this important? Because the covariance matrix of the multivariate Gaussian distribution is a very important design element for the Gaussian mixture models. So imagine that we would like to find a cluster for this example here. We see that this example here cannot be represented by a single probabilistic distribution. However, it's very likely that this example of samples can be represented by a collection of probabilistic distributions and especially by a collection of Gaussian distributions. So this could be a resulting clustering of this previous example, where these samples here can be assigned to the red cluster, while these samples here can be assigned to the green cluster, and we also have a blue cluster of samples. In order to go from this previous set that in which our samples were not assigned to this assignment, we need to answer essentially how can we assign the data to each Gaussian model, and also what parameters can we compute for each of these Gaussian distributions. Again, we will answer these two questions using an unsupervised learning algorithm. So as part of this unsupervised learning algorithm, we can assume that we have a probability for each sample being assigned to each of these three distributions. So we have a probability that our X sample is being assigned to the red distribution, another probability that the X sample is being assigned to a blue distribution, and another probability that the X sample is being assigned to the green distribution. We also can compute a marginal distribution for X, which is essentially the sum of all the separate probabilities multiplied by this prior. And this prior is the prior probability for each of the three mixtures. So having said that, what we need to do is that we also need to put this in a mathematical form. So the probability of observing a sample X is equal to the sum over all Gaussian mixtures. In this case, we can have K mixtures, and each term of the sum is equal to the product of the prior of the mixture, pi of K, multiplied by the probability of sample X belonging to the mixture K. That probability is modeled by a multivariate Gaussian distribution, and each mixture has a multivariate Gaussian distribution of mean mu K and covariance sigma of K. So the important thing here is to estimate the prior pi of K and mean and covariance mu of K and sigma of K for our Gaussian mixture model based on the data that we have. And in order to do this, what we need to do is that we need to assign each of our samples to some Gaussian mixture. Now, what we're going to do here is that instead of having a hard assignment where each sample is only assigned to a single mixture, we're going to have a probability of assigning sample N to a Gaussian mixture K. This probability is called responsibility and is being denoted by this term gamma of C and K. And it denotes again the probability of sample N belonging to mixture K. The sum of all these responsibilities for a single sample should be equal to 1, meaning that a single sample should be assigned to each of these mixtures, and this sum should be equal to 1. So if we assume that this responsibility is known, then we can estimate the parameters of the Gaussian distribution. Because again, if we assume that we know to what extent each of our samples belongs to each of the Gaussian mixtures, then we can simply, for example, estimate the prior of each of the Gaussian mixtures by just the sum of the corresponding responsibilities. And this term here in the denominator is the overall sum of all the responsibilities for all our samples and all our Gaussian mixtures. In order now to estimate a mean for each mixture K, we are going to find the mean by averaging the samples, each of the samples that belongs to the Gaussian mixture K, and by multiplying each of these samples by its corresponding responsibility. This will allow us to have a different contribution of each sample for that specific Gaussian. And again, this denominator here is just to normalize the mean for the data. And essentially normalize this responsibility here. Finally, the covariance matrix can be thought as the covariance matrix of each sample from the mean of the corresponding cluster. So essentially how far away each sample is from that specific mixture of the Gaussian. And again, this covariance is being multiplied by this responsibility of that corresponding sample. We have, in this case, we have estimated the mean, covariance, and prior of each Gaussian mixture by assuming that we know the responsibility of sample Xn for each Gaussian component. However, in practice, we do not know that. We have to go now an extra step and compute that responsibility on a probabilistic function. And the way to do this is essentially to see what is the probability of sample Xn belonging to its mixture K with mean mu K and covariance sigma of K. This probability, which is the probability of the multivariate Gaussian distribution, is also multiplied by the corresponding prior pi of K. And again, this denominator here is for normalizing these probabilities. Again, you will see that this responsibility now depends on the mean and covariance matrix for each of the Gaussian mixtures. So we cannot compute this unless we know our Gaussian mixtures. And reasonably, what we can do in order to compute both the parameters of the Gaussian mixtures as well as the responsibilities for our samples is to follow an iterative procedure, very similar to the procedure that we had with our k-means algorithm. So as an initialization step, we can just randomly initialize the prior, mean, and covariance for all our for each of the Gaussian mixtures. This initialization can be also the mu and the mu of the k-means algorithm if we just run a single k-means in our data. So as a step one, which is called the expectation step, since we have assumed some mean and covariance and priors for our model, we can compute the responsibility for each sample belonging to each mixture. And that responsibility is basically found using this equation here. Following that now, since we know the responsibilities, we can update the parameters of each Gaussian mixture. And this update is being done using these three equations here. This procedure can be iteratively repeated multiple times until we have a solution for our data. So this is an example of how we can run what we call expectation maximization for our GMM algorithm. First, we first randomly assign a mean, a covariance, and prior for each of our two Gaussian mixtures, as represented here by the red and the blue colors. So as a first step, we compute the responsibility of each of our samples belonging to each of the two Gaussians. We can see here that for these samples, the responsibility of them belonging to the red Gaussian is higher compared to the responsibility of belonging to the blue Gaussian. That is why these samples have been marked by the red color. After we have computed the responsibilities, we go ahead and recompute the mean, covariance, and priors for the red and the blue Gaussians. And we see now that this is how the red Gaussian looks like, and this is how the blue Gaussian looks like. We go back and recompute the responsibilities as well as the means and covariance matrices through the expectation and maximization steps. And after repeating these steps a few times, this is the result that we are getting. So we can see here a slight difference compared to the example that we have run based on k-means. And the first difference here is that these Gaussians now, first of all, have a center, but also have this covariance matrix. And this covariance matrix is not a spherical shape necessarily, but this covariance basically represents the shape of the data. We can see here that the data has more variability across the x2 axis. Therefore, we would expect that the element that corresponds to the x2 axis of the diagonal of the corresponding covariance is larger compared to the element that corresponds to the x1 axis. This is another example where we have another set of samples that has been run through expectation maximization for estimating 4 Gaussians for this GMM model. And again, we see that each of these Gaussians has a different type of covariance matrix, a different type of directionality, and a different spread across the X and the X1 and the X2 axis. We also see a contrast between the k-means algorithm and the GMM algorithm for assigning the same set of data. So we see definitely that GMM algorithm is more flexible and can be applied in a more flexible manner to assign data to clusters. So an example here is the fact that for these specific data sets, we see that k-means again just assigns each of the data according to a hard thresholding, and also just assigns this data without understanding the spread across the x1 and the x2 axis. In contrast with GMM, we see that there is some notion of spread. Here, for example, we see that samples are spread more towards a diagonal line of approximately 45 angle degrees. Here we can see that the examples are mostly spread across the x2 axis rather than the x1 axis. And again, this is being reflected by the covariance matrices of each of the corresponding Gaussians of the mixture. Also, although this is not represented in this example, for Gaussian mixtures, we also have the responsibilities that reflect how much, to what extent each of these samples belong to each of these distributions. So there is an extra probabilistic step that can be very useful when we model our data.